Okay, today we're going to have a look at topic 7 of this course, special parts of a triangle. Because we have a lots of contents in this topic, so we'll divide it into two parts. And today we're going to have a look at part A. And in part A, we're going to have a look at bisectors and the concept of perpendicular bisectors of a triangle. And in our next lesson, we'll talk about part B, which include angle bisectors of a triangle, medians, altitudes, and some more challenging problems. Okay, first of all, let's have a look at the concept of bisectors. So in general, any line segment from a vertex of a triangle to a point on the opposite side is called a civilian. The perpendicular bisector of a line segment is a line passing through the midpoint of a segment such that the line is perpendicular to the segment. For example, in this figure, line K is called the perpendicular bisector of segment AB because first, it is perpendicular to the segment AB, right? And second, this line bisects segment AB because we have AM equals MB. If it's perpendicular to a given segment and it also bisects that segment, then that line is called perpendicular bisector of the given segment. Pretty straightforward concept, right? You get it? Okay, and there is another concept called angle bisector. The angle bisector of an angle is the ray that divides the angle into two equal angles. For example, if we have an angle AOB and there's a ray M, if ray M divides the given angle AOB into two equal angles, angle AO, for example, let's call this point P. Angle AOP equals angle BOP, then we call the ray M is the angle bisector of angle AOB. This is an example of angle bisector. Also, very straightforward concept, right? Any questions? Okay, then next let's have a look at some important properties related to either the perpendicular bisector or a angle bisector. Line M is a perpendicular bisector of segment AB. Can you show that if C is on M, then CA equals CB? Again, you should try to draw a diagram to help you think. So we can draw a segment AB, right? Point A is here, point B is here. And line says line M is a perpendicular bisector, so we can draw a perpendicular line to AB. So let's call this line M. M is perpendicular to AB and also it bisects AB. So let's call this point M. We have AM equals MB, right? Can you show that if C is on M, then CA equals CB? So C is an arbitrary point on line M. So let's just say C is here. Then can you prove CA equals CB? CA is here, CB is here. You prove that using what we have learned so far. Okay, I'll give you 1 minute to think about this, and after that, we'll have a look at the solution together, okay? You can use any theorem you have learned or proved to prove this statement. Sure. So if you want to use isosceles triangle, how do you know ABC is actually a isosceles triangle? You are actually trying to prove this fact, right? Okay, let's have a look at the solution here. But if you want to prove a pair of equal lengths, probably you'll use a pair of congruent triangles, right? So note that this side equals this side, and this angle is 90 degrees, this angle is also 90 degrees. It shares the same side here, right? Therefore, we know triangle AMC must be congruent to triangle BMC. Therefore, this side equals this side, right? Can you follow me? Okay, because AM equals BM, angle AMC equals angle BMC equals 90 degrees, and they share the same length. MC equals MC. Therefore, triangle AMC is congruent to triangle BMC, right? Therefore, corresponding lengths are also equal. So AC equals BC, or CA equals CB. So this does not matter where C is, right? For example, if C is here, 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 or here, the statement is also true, right? So that is an important property of the perpendicular bisector. Any point on the bisector of a segment it's equidistant to any endpoint of the given segment. And the problem is the reverse statement is also true. For example, can we say if AC equals BC, then C must be on the perpendicular bisector of segment AB. Can you also see that? Can you see the difference between these two statements? First statement is given M is a perpendicular bisector and C is on M, then we have CA equals CB, right? And reverse statement is if you know AC equals BC. So for example, we have a segment AB. If we know AC equals BC, can you conclude C must be on the perpendicular bisector of AB? Or can you prove that? Again, I'll give you 1 minute to think about that. And after that, we'll have a look at solution together. Okay, have you finished? So how do we prove that? If you want to prove C is on the perpendicular bisector, you need to prove that this line is perpendicular to AB and this line is actually bisects AB, right? So we could first connect C to the midpoint of AB. So we can let point M be the midpoint of segment AB. Then connect CM. Then as long as you can prove CM is perpendicular to AB, then CM is the perpendicular bisector of AB, right? So because we know AC equals BC, this side equals this side, and we also know angle. Okay, we need to prove that angle is perpendicular. So next one, we know AM equals BM, right? And also they share the same length, CM equals CM. Therefore, we know triangle AMC must be congruent to triangle BMC according to SSS congruence, right? Therefore, we know angle CMA must equal angle CMB, which is 90 degrees, right? Therefore, we can prove C must be on the perpendicular bisector of AB. You see that? So that actually tells us the statement here can be reversed. Reverse statement is also true, right? So you could say, first, okay, what is the first statement? I'm in the perpendicular bisector AB. Okay, we could say C is perpendicular bisector of AB. Then we have CA must equal CB, right? This is according to the previous example, right? And according to this second example, we have, if you have CA equals CB, then we could say C is on the perpendicular bisector of AB. This statement is reversible, right? And in mathematics, we have a special notation for this. So if you have a reversible statement, you could use a simple symbol here. C is on perpendicular bisector of AB. If and only if two directional arrows CA equals CB. So this summarizes these two statements together. Do you get it? And it read as if and only if, which means you could go either way. Did you get it? Or sometimes you could also use this symbol, IIF. IIF means if and only if. Or if you don't like that, you could use this symbol. Bidirectional arrows. They are actually the same thing. Oh, sorry. My bad. It's not IIF. It should be IFF. IFF. If and only if. And as we go through the remaining lessons, we're going to have a lot of if and only if statements. Okay, we'll talk about this if and only if later in our class. Okay. So the previous two examples tells us that the perpendicular bisector of a segment is a straight line consisting of all points that are equidistant from the endpoints of the segment. So this is one of the important properties of the perpendicular bisector. Did you get it? Again, draw a diagram to illustrate this situation here. Suppose we have x, y, z is the angle, and an angle bisector here. Any point, for example, we have an arbitrary point C on the angle bisector. Can you prove that C is equidistant from yx and yz, which means if you draw a perpendicular line here, let's call this point is Q, draw another perpendicular line here, CP is perpendicular with xy. If YC is angle bisector of XYZ, can you prove CP equals CQ? Have you finished? To prove this is relatively easy, right? Because we can use triangle YPC that is congruent with triangle CYQ because they share the same length. You have a pair of equal angles and another pair of angles here, right? So we could say because angle PYC equals angle QYC and YC equals YC, angle YPC equals angle YQC, which is 90 degrees. Then we have triangle PCY is congruent to triangle QCY according to AAS, right? Therefore, we know PC must equal QC, right? Okay, and that proves that any point on the angle bisector is equidistant from both sides of the angle. And now think if the reverse statement is also true, which is similar to the perpendicular bisector. If see the point inside angle XYZ such that C is equidistant from YZ and YX as shown, can you prove or show C must be on the angle bisector of angle XYZ? So basically, first you need to connect Y and C, right? So first of all, let's connect YC. And we need to prove YC is an angle bisector of angle XYZ, which means you need to prove these two angles are equal, right? Again, probably we'll use a pair of congruent triangles. So we could say because PC equals QC, right? And YC equals YC. And we also know YP is square root of YC square minus PC square. YZ equals square root of YC square minus QC square, right? Therefore, we know YP must equal YZ, right? And therefore, if this side equals this side, this side equals this side, PC equals QC, and share same lengths here, then we could say triangle PCY must be congruent to triangle QCY, right? According to SSS. Therefore, we have proved angle PYC equals angle QYC, right? Therefore, we have proved if PC equals CQ and C is inside angle XYZ, then C must be on the angle bisector of XYZ. No matter where C is, it must be on the angle bisector of that angle, right? You see that? So if we consider both of the examples here, then we can conclude that the angle bisector of an angle consists of all points that are equidistant from the side of the angle. This is an important property of the angle bisector. Okay? Did you get it? Alright, then we have talked about the concepts and properties of perpendicular bisector and angle bisector. So now let's consider a quick quiz. Okay, I'll give you 2 minutes to think about this by yourself, and after that we'll have a look at the solution together. Okay, so we have a line M, which is a perpendicular bisector of both AB and CD. Which of the following must be true and why? So if you think that must be true, you need to prove that. Otherwise, as long as you can give a counter example, you can say that's not necessarily true. Or if you prove it must be false, you should also give your proof here. Okay, I'll give you a hint. So first of all, it's better to draw a diagram to talk about the situation here. So suppose this is AB, and there's another segment CD, right? M is perpendicular bisector of both AB and CD. That means M is here. Okay, you can start now. So apparently A is not correct, right? For example, you could look at the diagram here. Suppose AB has a length of 4. We could let CD be 2, right? As long as M is a perpendicular bisector of AB and CD, they could have different lengths, right? Or simply speaking, if you extend AB to some point C and D, in this case, AB is not equal to CD, but still M is a perpendicular bisector of both AB and CD. So how about B? If M is a perpendicular bisector of AB and CD, then this angle must be 90 degrees. This angle is also 90 degrees, right? And corresponding angles are equal, indicating AB must be parallel to CD, right? So the second statement is true. And first one is false. AB can be different, can have different lengths with CD. Any questions? All right, next let's have a look at perpendicular bisectors of a triangle. Okay, we're going to use an example to illustrate the concept here. Can you show that the 3 perpendicular bisectors of a size of a triangle are concurrent? Concurrent means they meet at a single point. Show that there is a circle centered at this point that passes through all 3 vertices of the triangle. Okay, I'll give you 5 minutes to think about this question, and after that, we'll have a look at the solution together, okay? Okay, do you have any ideas? Okay, again, we can draw a diagram to illustrate the situation here. So suppose we have a triangle ABC. Well, if you want to prove three lines are concurrent, it's usually not that easy, right? So usually we'll consider two of the lines. So suppose we have the perpendicular bisector of AC is line L. Perpendicular bisector of AB is line K. And these two lines intersect at point O. Then we wish to show that O is on the perpendicular bisector of BC, right? So we could say let L be the perpendicular bisector. I'll just use PB, okay, of AC, and let line K be the perpendicular bisector of AB. L and K intersect at point O. We wish to show O is also on the perpendicular bisector of BC. Okay, since O is on the perpendicular bisector of AB, then we know OA must equal OB, right? And because O is also on the perpendicular bisector of AC, then we know OA must equal OC, right? This is according to the property of perpendicular bisector. Then we have OB also equals OC, right? If OB equals OC, again, according to that theorem we have just proved, if this side equals this side, then O must be on the perpendicular bisector of BC, right? You see that? Therefore, we have proved O is on the perpendicular bisector of BC, right? And therefore, the three perpendicular bisector are concurrent at point O, right? That completes the first statement. And then if we have OA equals OB equals OC, then we can use this lens to draw a circle, right? If you use a lens OA, OB, or OC to draw a circle like this, then A, B, and C must be on that circle, right? Because any of OA, OB, or OC is the radius of that circle. So if you draw a circle that's centered at O with radius OA or OB or OC, the circle will pass through B and C and A. Therefore, the point O and the circle described can prove this statement here, right? So if you draw a circle centered at O, radius equals OA, then we have shown that there exists a circle that can pass through all of the three vertices of the triangle. That completes the second task, right? So this example shows us the following important property. The perpendicular bisector of the sides of a triangle are concurrent at a point. This point is called circumcenter. The circle centered at circumcenter that passes through the vertices of the original triangle is called the circumcircle of that triangle because it's circumscribed about the triangle. which means it passes through all the vertices of the triangle. And finally, the radius of this circle is called the circumradius. So we have a few trivial concepts here you should remember. Okay, circumcenter, circumcircle, and circumradius. Circumcenter is usually labeled with letter O, and circumradius is usually called uppercase R. Okay, I'll give you 1 minute to have a look at the concept here. Okay, what is circumcenter, what is circumcircle, and what is circumradius? All right, next let's consider a exercise. Where is circumcenter of a right triangle? What is circumradius of a right triangle? Can you make a reasonable guess and prove your reasoning? Okay, any ideas? So if you draw a right triangle by yourself, suppose we have a right triangle x, y, z. First, if you draw a perpendicular bisector on this side, then on this side, seems that the circumcenter is somewhere here, right? Seems that it's a center point of the hypotenuse y, x, z. Then can you prove that actually true? So K is the midpoint of xy. L is the midpoint of x, is the intersection between the perpendicular bisector M and xz. So can you prove L is actually the triangle xyz's circumcenter? So according to the setup here, since M and YZ are both perpendicular to XY, we have M must be parallel to YZ, right? Therefore, we have triangle XKL must be similar to triangle x, y, z, right? According to AA similarity. Therefore, we know xk over xy must equal xl over xz, which equals 1 over 2, right? And that actually proves this side equals this side, xl equals zl, right? Therefore, L is the midpoint. And if L is the midpoint of xz, apparently L is also on the perpendicular bisector of xz, right? Which means L are on both M and perpendicular bisector of xz. We already know that all of the perpendicular bisectors will intersect at one point. So L must be the circumcenter, right? Did you get it? And the endpoints of hypotenuse are vertices of the triangle. So by definition, they are on the circumcenter, right? As they are on the circumcircle, right? Which means if you draw a circumcircle here, then x, y, z are on the circle. Then actually LZ and LX and LY are the radius of that circle, right? So we know the radius of that circle is 1/2 of the hypotenuse, xz. Did you get it? So there is a special case for the right triangle. Actually, the circumcenter is located halfway of the hypotenuse, and the radius of the circumcircle equals 1/2 of the hypotenuse. So this is an important property of the right triangle. Circumcenter of a right triangle is the midpoint of the hypotenuse, and circumradius equals 1/2 the length of the hypotenuse. And there's another theorem, similar theorem you can prove by yourself. For example, suppose this is the diameter of a circle. If you have a circle, if AC is the diameter of the circle and B is any point on that circle, you can actually prove that angle ABC must be 90 degrees. Why is that? Because if you connect B and O, well, let's call this number 1, angle number 2, angle number 3, and angle number 4, right? Because we have angle number 1 plus equals angle number 2 and angle number 3 equals angle number 4, right? And we also know that angle number 1 plus 2 plus 3 plus 4 equals 180 degrees. Therefore, you can actually prove that angle 1 plus angle 3 equals 90 degrees. That means the angle here corresponding to the diameter in a circle must be 90 degrees. Did you get it? So you can use this theorem together. Do you have any questions? Alright, then if not, let's consider another example. A two persons, Ariel and Zeppa, play Name That Circle game. In this game, Ariel imagines a circle drawn on her shaded paper. Zeppa can then ask for points that are on that circle. Zeppa wins when he can draw that whole circle. There's 3 questions. A. Can Zeppa win the game if Ariel only gives him 2 points? B. Can Zeppa win if Ariel gives him 3 points? Or C. If Zeppa asks for 4 points, Ariel isn't really paying attention and just picks out 4 points at random on a piece of paper. Zappa tries and tries, but he can't name that circle. Finally, he insists that there is no such circle. Could he possibly be right, or should he just try harder? Well, actually, the nature of this question is asking you how many points can actually determine a circle, right? In question A, can 2 points determine a unique circle? Clearly, 2 points isn't enough, right? Okay, let's have a look at the question together. Why it's not enough? Because we could have a situation like this, right? If you have only 2 points A and B, we could draw in the infinite number of circles that crosses 2 points. So 2 points cannot determine a unit circle, right? So how about 3 points? Can 3 points determine a unique circle? I mean 3 nonlinear points. If the 3 points are collinear, you can't draw any circle, right? Collinear means they're on the same line. If 3 points are on the same line, you can't draw any circle. But if 3 points are nonlinear, we can actually first draw a triangle, right? We know the triangle has a circumcenter. So use that circumcenter, we can draw a circle there, and that circle is unique. So given 3 points, Zappa can name that circle. He can connect the points to make a triangle. Then he can draw the perpendicular bisectors of any 2 of the sides of the triangle, right? Where they meet is called the circumcenter, and then he can make the circumcircle. Notice that the 3 points must be non-collinear, which means they cannot on the same line. The center of any circle that passes through all 3 points must be on all 3 perpendicular bisectors of the sides of the triangle with these points as vertices. Therefore, the circumcenter is the only possible center of a circle through the 3 points, which means the circle is unique, right? Therefore, the circumcircle is the only circle that passes through all 3 points. Did you get it? And how about 4 points? So suppose we have 4 points here. We know that 3 non-collinear points can determine a circle, right? But it does not necessarily pass the 4th point, right? Did you get it? So let the point be A, B, C, and D. As described in the previous part, there is only one circle through A, B, and C. But this circle doesn't have to go through point D. For example, we could pick another point here, which is outside circle. If we pick out 4 points at random, there doesn't have to be a circle that passes through all of the 4 points, right? So Zappa should give up once he sees that circle of ABC doesn't pass through D. One such arrangement of points is shown here in this diagram. Okay, this tells us one important conclusion. Just as 2 points determine a line, we have now shown that 3 non-collinear points determine a circle. So if you have 3 non-collinear points, you can draw a unique circle that passes through these 3 points. This means that given any 3 non-collinear points, there is exactly one circle that passes through all 3. Any questions? Okay, 2 points determines a line, 3 non-collinear points determines a circle. Alright, then let's consider one last example, then we can conclude this lesson. Can you find circumradius of an equilateral triangle with side length 6? Alright, let's have a look at the solution together. So if we have a equilateral triangle, ABC, then we can draw a perpendicular bisector of the side BC and draw a perpendicular bisector of the side AC, right? Suppose they intersect at point O, then we can connect OC, right? Then in this right triangle and in this triangle, they share the same length here. And we also know that CP equals CQ, right? And because both of them are right triangles, we also know the other pair of the sides are also equal, according to Pythagorean theorem, right? Did you get it? Okay, I'm not gonna write all of the statement here. You should write this by yourself. So according to the discussion here, we have triangle OCQ is congruent to triangle OCP according to SSS, right? And then we have angle OCP equals angle OCQ equals 30 degrees, right? Then consider this triangle here. This is actually a 30, 60, and 90 triangle, right triangle, right? So if you know the set length is 6, then CP equals 3, right? Suppose let OP equals X, then we have OC equals 2X, right? Then we have X squared plus 3 squared equals 4X squared. This gives us 3X squared equals 9. Then X squared equals 3. And X equals square root 3, right? Therefore, the radius of the circumcircle, which means circumradius, is 2x, which means 2 square root 3, right? Okay, because we don't have letter R here, so let's just say circumradius OC equals 2 square root 3. You get it? Okay, and after this lesson, I'll give you my notes and today's homework to you to Google Classroom. You can download it from their